Hi everyone, Oskar Świerat here. Welcome to the part 2 of the tutorial about graphics pipeline for Unreal Engine 4. In this video, I will explain the general graphics pipeline of modern GPUs and what you should learn to be able to find bottlenecks in your scenes and places you can optimize. Before we begin, we should be able to define the problem. Is our frame drop happening in a certain area? In some specific game scenario, for example, some barrels exploding or some enemy entering the area, or maybe on a hardware of a certain vendor. Then as we proceed, we should isolate what we are testing. To come with a meaningful test, we have to be able to make assumptions. So that's why it is very important that you learn about the rendering pipeline, both in general on the GPU and in Unreal itself, because each engine has its own path, its own potential problems. I encourage you to approach it like a scientist. Make observations, what's happening in your scene, which areas cause the trouble, then formulate some hypotheses, like for example, I think that translucency is the biggest problem. Then you should be able to develop some testable predictions, like put your camera in a fixed place, insert a translucent heavy object, measure performance, delete the object, measure performance again, and with this approach you will be able to gather data to test your predictions. Now let me proceed to the anatomy of a frame. To display a frame, both calculations on the CPU and the GPU had to be finished. So all the game code has to be computed, all the pixels have to be shaded, and so on, and only then we can dispatch a frame to the screen. That's why the cost of a frame, the time it takes to show a frame, is the bigger number of either CPU or the GPU. If the GPU finished first, then it will wait for the CPU to dispatch new commands for the GPU. While if the GPU is taking too long, the CPU has to wait for it. If you press tilde and enter stat unit, you will be shown these values you can see here. On the GPU, we have concepts of parallelism and the pipeline. If something is parallel, it means that multiple cores, hundreds or thousands of cores, work on the same task simultaneously. So obviously, cores are best utilized when they are working on the same task. For example, the same big triangle that is shaded with a single material. This is important because all cores assigned for a specific task on the GPU have to be exactly in the same place. For example, exactly the same moment of the shader. Now, pipeline is like an assembly line. So the frame is divided into steps, and for example, the vertex shader passes the data further to the pixel shader where the pixels are computed, and only then it is passed onto the screen. So this means that the pixel shader can't continue before it's fed with data from the vertex shader. Now the simplified graphics pipeline on DirectX 11 and OpenGL looks like that. We start with providing vertices to the vertex shader. It does its transformations. Then comes the tessellation phase, the geometry shader, which is the only one we have no direct access to as an artist in Unreal Engine. And last comes the pixel shader, which is responsible for materials, lighting, and post-process. An important thing that can really affect your frame rate are the draw calls. So draw calls are the commands sent by the CPU to control the GPU. So for example, commands like change my mesh or change my material. Because if you want to draw a triangle set with a different material, different shader, you have to dispatch a command from the CPU first, which then goes through the driver, only then is translated, and only then it's submitted to the GPU. So having a lot of materials, a lot of different separate objects, is a lot of work for the CPU. You can check your amount of draw calls by pressing tilde and entering stat scene rendering. Now let me explain pixel-bound sources of trouble, because pixels are most probably the slowest part in your pipeline. The bigger the resolution, the more pixels we have to be shaded, unsurprisingly I think. So heavy lighting, which is done per pixel, heavy shaders, and also post-process effects depend on the resolution of the screen. And given the current Full HD and 4K resolutions, this can really mean a lot. So how to check if we are pixel bound? While running our game, we can press tilde and enter r.screen%, for example 25, or r.setres 480 by 270, for example. Then if your frame rate improved a lot, then it means you are pixel bound, not for example Vertex-bound or memory bound. The pixels are the problem. The biggest common problem with shading pixels is translucency. Opaque is very cheap, because only the mesh that is closest to the camera is being rendered. While when you have translucent object, you have to draw everything. The translucent object, the next one behind it, sometimes even the next one, and only then the rest of the scene. So it's a big cost, and of course translucent particles can be an unexpected but very heavy source of computation. So you can use not only level of detail on the meshes, but you can also do level of detail on particle emitters. You can have very detailed translucent particles when you are nearby, but as you go further away from the emitter, you can replace them with some more crude particle systems with fewer particles to minimize the impact on performance. Now, an unexpected source of performance issues that I think is not so well known among artists, while it should be, is the so-called quad overdraw. This is the reason why small polygons waste GPU time. In this case, a quad means a block of 4 pixels, 2 by 2. And most of the operations on the GPU, when it comes to pixel shading, are done on full quads, or even bigger tiles, like 8 by 8, not on single individual pixels. It's easier for the GPU, or sometimes necessary for the GPU, to perform operation on bigger tiles and only then discard the unnecessary pixels. So the discarded pixels are basically wasted. As you can imagine, the smaller the triangle, or more thin the triangle, the bigger the problem. So the triangle count itself is actually not a problem very often. Quite contrary to the popular opinion, the triangle count by itself doesn't matter. It's much more important to avoid small and thin and long triangles. Use level of detail for that to control this. Try to keep polygons big and even in screen space, so watch for it from your camera, from your game, not just the 3D package. And empty pixels in foliage are extra waste, because you have translucency or some overdraw, so clip like crazy. Spend more polygons, but keep closer to the actual shape of the plant to be drawn. So back to the triangle count. Is it really not a problem? Mostly it isn't, but keep in mind that it can explode after tessellation. When you don't control tessellation too well, or assign too big values, you can end up with a lot of quad overdraw. And the amount of vertices matters for shadow casting, because a lamp that has some meshes on its way needs to sort of make the copy of the mesh to draw a shadow map. So the more vertices, the bigger the problem. Now this is a nice thing to keep in mind, but don't think about it too much. It's just good to know that hard edges, or smooth groups, or splits on your UVs, they add to actual vertex count, because the information has to be stored several times for a single point, single vertex. But it only affects memory usage or disk space, not the actual rendering performance. So as I said before, dynamic shadows can be a vertex-bound source of trouble. The heavier meshes the light has on its way, the bigger the performance cost. So to avoid it, it's best to disable dynamic shadow wherever you can. Probably for many of your lights you don't need dynamic shadows, or you can change them to static. Then it's also a very good practice to keep the attenuation radius as small as you can. This will not only limit the cost of shadowing, but also the cost to render the light in pixel shaders. Now, what issues can we encounter when dealing with the memory? The first thing is that too many texture samplers in a material use up the bandwidth. And the bandwidth is the amount of data that can be transferred between memory and the actual cores that perform the calculations. So compression helps a lot. Compression is supported directly on the GPU, so don't disable it in your textures unless you need it. And the so-called texture packing helps too. It helps you to save on the amount of texture samplers and to optimize when it comes to memory. It means that you take, for example, 3 grayscale textures like roughness, metalness, and ambient occlusion, and pack them into specific channels of a single RGB texture. So each one occupies only a single channel, then you can store them like a single texture. The GPU tries to keep last access areas of a texture in the cache. So the cache is a very fast memory that is located very close to the actual cores that perform the computations. So instead of going all the way to the RAM memory, it can fetch the data it needs from the nearby cache. So if you want the GPU to use the cache, which is very small, keep the UV continuous. I know that some clever shader tricks can, for example, jump on the UVs for some noisy effects or something like that, but use it sparingly, keep that in mind, because this is not what GPU expects and it can waste the cache. But normally, with standard art and materials, you should be fine by default. There is also the streaming cache. It's not related to the cache on the GPU, it's a cache in normal RAM that is maintained by Unreal. This is like a storage of textures that can be loaded at once. So too many textures in a level, and remember that light maps are textures too, can fill the cache. Unreal will try to load the lowest possible resolution, the lowest resolution of a texture that is needed. For example, some far away object doesn't need the biggest resolution to be loaded, but after the cache is full, you can encounter the same behavior even on close objects, because it can't load any more textures. So press tilde and enter stat streaming when you see such behavior in your scenes. Currently, Unreal has 2 ways of rendering lighting. One is called deferred rendering, and it is the default method, and the second is called forward rendering. The forward rendering is an older technique, but it was recently optimized, so it's now called forward plus quite often, this new approach to forward rendering. And the deferred rendering means that all the data are collected first per pixel, for example normals, normal maps, roughness, base color, and only then, in a kind of post-process, the light is rendered using this data. So only the actual pixels on the screen are being lit. It also applies to reflections, but there is a significant limitation that if we only draw the closest pixel to the camera into the final buffer, we have no way to render transparent objects. So this is when forward rendering kicks in. So in the standard default settings, you have actually both engines working at once. You can switch to only use the forward rendering. It can be helpful because it can lower the cost of the memory you need to store all the buffers and the final result of the screen. And it's useful when you have a statically lit scene. For example, for some VR projects, you probably can't afford too many dynamic lights anyway, so it can be helpful to switch to forward. While if you have many light sources, it can be cool to stay with the default deferred rendering. It doesn't matter for shadows, it only matters for the direct lighting. Now let me show you some optimization view modes. Okay, so this is our test scene again. In the upper left corner, press lit, go to optimization view modes, and here we have them. These are our basic tools to check some performance issues before we proceed with the actual profiling. So for example, this one is light complexity. Light complexity shows us the radius of each particular light, and we can see them overlapping. Let me move this light away. As you can see, this is the area that is affected by the light. Okay, now it should be better. So this is this light's area of influence. If I copy the light you can see how the cost increases in the place where they overlap. That's because the pixels have to be shaded with two sources of lighting. Obviously, more lights overlapping mean more troubles with performance. Here is the particularly bad area, so a good place to change some lights to static or just delete them. Another interesting mode when it comes to the complexity of rendering pixels is shader complexity. Now you can see that this area is very, very bad when it comes to the heaviness of shaders. That's because the cost of shading when it comes to translucent objects is, as I said, not only the closest one, but all the objects behind. So this is a sum of the cost of shading of all the objects from camera up to the end to the camera visibility. That's why if we have only some translucent things overlapping, it's not that bad. But as we go further with the amount of additional planes being blended together, we start to have a problem. As you can see here, when I go back to shader complexity, it's extremely bad. Now in optimization Viewmodes, we also have the quad overdraw. This is the problem that I mentioned earlier. As you can see, it shows a general overdraw, not just the quad overdraw problem. So when we have multiple translucent things in behind each other, it goes all the way to white. But for example, our level of detail settings for the asteroids seem to be set to a bit too high, because we have very small polygons frequently overlapping each other. This building is very well optimized, because we have almost no overlapping here. Now let me disable the grass. Come on, grass. Disappear. Thank you. Currently the tessellation of the landscape is quite fine, but if you ever have some problem with that, then there is a thing you can do. Go here to Landscape, Manage Mode, the Selection tool for components. Select the components that you think that have too many triangles, and in the Details tab, go to Load Bias and set, for example, 1 or 2, or sometimes even higher. And as you can see, the amount of vertices used decreased. This is a very good practice to lower the amount of triangles in your landscape, except for the areas that really matter. When it comes to memory, an interesting optimization view mode is light map density. This mode shows the size of the actual pixels of light maps that will be calculated and stored. So the landscape has quite a low resolution, and it's okay because the entire landscape is big. And remember that light maps are stored for each object separately. Each instance of the same mesh will get its unique light map anyway, because it stores lighting, which is different for all the places in the scene. So, if you're not careful, this can really explode into huge numbers. And the light maps don't have to be too detailed. They can be quite blurry most of the time. It's better to change your idea for lighting a bit, or use some smoother shadows, than, for example, to increase your light map density. Here each module has 32 pixels, I think. now 64. As I change it, you can see how the density of pixels increased. And the color changes through green all the way to red. Another way to check how well you are going with the amount of textures used is to go to Window, Statistics, and this window pops up. This window pops up when we see all the textures and you can sort them by the amount of memory used. For example, this material is 2K by 2K, but its current usage, the usage that was really loaded into the streaming pool, is just 64 by 64. Probably it's used only by some small object. I don't know which, so I can check it here. Okay, some asteroid is using this texture in a very low resolution. Now, if I want to suppress the resolution anyway, I can click on the texture name. It shows up in the content browser, then open it, and in the compression tab, I can expand this setting and say, for example, maximum texture size 256. As you see, the resolution lowered, and this is a very good method to control your resolution without going to the actual texture editor. You can change it anytime. Max in-game is shown as 512. So thank you for watching this part about the GPU pipeline and optimization view modes. Please try this stuff in your projects. If you get stuck, ask in the comments. If you know the answer, help each other. In part 3, I will show you the tool that is called GPU Visualizer. You run it by pressing Ctrl, Shift, Comma, and with the knowledge you acquired in this video, you will be able to examine your scene pass by pass. For example, here, the pass of light rendering is my biggest cost. We'll dive into this in the next part. Thank you again for watching and see ya!